So today, I think you will learn the concept of this, the data mining, also big data, and also know the career for some. Okay. So would you please welcome Dr. David on the stage?
Thank you. Thank you very much for inviting me to talk to Professor Conrad and to the MITL. It's nice to be on campus. My wife's alma mater, so it's nice to see the place. And the facility looks really beautiful, and the hardware that you can play with in the lab looks interesting to me because I spent a long time in computer engineering classes, but I never managed to do one that played much with hardware. So I think it's really interesting. But I hope I can convince you today that that working with software, and in particular with data-driven analytics and software algorithms and mechanisms is also really promising and can be as interesting as hardware. Okay, so the title of the talk today, as you can see, is Data Mining, Big Data, and careers in companies that are built on data mining and big data. Okay. So the outline of the talk, first I'll just tell you a little bit about my background so you understand where I'm coming from and some of my experiences. And then some motivation. Why should we care about data analytics? And the knowledge discovery process of starting with raw data and getting to actionable knowledge. We'll talk about some common data mining tasks. So what are things people typically do when they do data mining? And then some examples of some of those tasks so that you get a little bit of an idea of not just how are we trying to get the computer to recognize patterns or group or organize things, but what are some examples of the most common algorithms that people use to do that. Then we'll talk about big data, because scaling things up to be able to handle big data, as you know, of course, a very hot, relatively hot new topic of how do we take this web scale data and get knowledge from it. We'll talk a little bit about distributed computing, so how big data processing systems get their work done, the kind of challenges we have and opportunities. And then we'll shift gears a little bit and I'll give talk about some experiences from industry. Mine are at working at really, really big tech giant companies, and then all the way at the other extreme working at really tiny tech companies. But both of them built on data mining and data analytics. So hopefully I can share my experience and that can help you. And then lastly, some tools and resources in case you're interested or come across some of these problems in the future. Okay. If you have any questions as we go, please just ask them during the talk. Don't wait till the end or anything. That would be great probably then. Okay. So about me, again, my name is David Fuhry. I got my PhD in computer science and engineering at Ohio State University. It's in the USA. And my research interests there, data mining, database, high performance computing, similarity search, which is finding things that look like other things in large data sets, and visualization. So how do we, once we have some results, how do we present complicated things back so that people can understand them and work with them? Kind of some of the things I'll be talking about today are internships at Google and at Twitter in 2012 and 2013. So both of those were in the Bay Area. So maybe I can tell you things about just sort of what that's like, being in that environment, what companies are like, how to be successful there, and some tips I can give. And then at the other extreme, I co-founded an information aggregation company. So hopefully I can tell you some things about how you might start from an idea, and you think you're onto something, you can produce something that people want, and to actually go through the process of trying to build something that you can sell to people, and maybe some of the difficulties along the way, and how to get through some of them. Okay. So why learn data analytics? What's the motivation? Well, probably you know and have heard that it's quite a hot topic, right? Between data science and then a lot of the more traditional areas, machine learning, data mining. You hear these all the time in tech news, many companies, that really any company that has a lot of data, has a lot of interest in having skilled people who are able to come into the company and get some more value out of that data. Help them do whatever they do better, faster, cheaper by looking at information that's been collected. And there's a lot of reasons that this has become the case more recently, right? There's a lot more capability in our systems and things like that can now support these kind of operations, but we just need people to get there and get the good ideas and think, try a few things, and try to get good results. So this is kind of at all different scales, from the typical tech giants, giant companies that we know they have a lot of data, and their whole business is built on doing things well with that data for the users and customers. But even companies that are not known, of course, for technology, businesses of all sizes, they have a lot of information. Telecommunications companies have lots of people making calls and buying their services, and they want to know how to optimize their systems. Finance companies like banks and credit cards, they have a lot of people making transactions. They need to prevent fraud. They need to try to keep up with marketplace conditions. Manufacturing or making things, they want to make the things better, faster, cheaper. And for all these companies, we've often collected a lot of data and then would be interested in taking it and making better use of it to improve their processes. So big data and data mining are transforming almost every industry out there. And even if you don't take a personal interest in data analytics, I think there's a very high chance, just being in our industry, you're going to be working with people who are someday. So shoulder to shoulder with data scientists, with people trying to run these kind of algorithms and do these kind of processes. And it will be good if you're able to be helpful to them by contributing what you know, putting your heads together to solve problems. Okay, so that's some good reasons to learn data analytics. And here's the goal of what we're trying to get after here. So the so-called knowledge discovery process. The idea is we start with raw data. You probably lives in databases in an organization. And you can see where we want to get on this staircase is all the way up to the upper right and get knowledge from this data. So there's a lot of steps in between. So typically they involve something like, we have the data, we need to kind of clean and filter it and get some pre-processed data. And then depending on what you want to be trying to do, you're likely to need to transform that data into a format that your processing algorithms, your tools can take as input. Then after those transformations, do data mining. Use data mining or similar analytics tools. And then we get some output. Right? But we're not done yet, because the output in terms of graphs, numbers, things like that, we still need to apply our intuition to interpret it and figure out how to best utilize it, fix problems with it, try to understand it better, until finally we end up with actionable knowledge, decisions we can make based on the data that are the right decision to make. And you can also see throughout this process, it's iterative, so it repeats. And at many stages throughout this process, we're likely to look at the results and think, well, they're partly right, but there are also some things that don't seem right with them, or we're curious, so let's check. And in doing that, we can often see ways that, okay, if we go back a step and repeat our process with some changes, we can do a better job coming forward. So this knowledge discovery process is typically iterative for a lot of reasons. Okay, so this is our goal. And what we've seen in recent years, one of the biggest trends is, as we've said, the data is growing a lot, right? So instead of small databases, now we have huge amounts of information. And that's going to affect everything else that happens in the pipeline, right? All of these processes need to scale up to the level of that information. Otherwise, we won't be able to make use of it. And so that is going to cause us to perhaps to rethink certain parts of the operations. So that's the big data part of what I'll talk about today. Okay, so data mining, you can see here the core of the knowledge discovery process. And big data, we're saying it's the modern source of knowledge discovery. A lot bigger data. Let's try to discover knowledge from it. Okay, so then first we'll talk about data mining, and then we'll talk about big data. So within data mining, we'll talk about some of the common things that people do. So if we say data mining as opposed to certain other fields, some of the most common tasks are clustering. So that's grouping things. So we can imagine we have a lot of data, and we want to figure out what are the groups in this data. Second, classification, which is also called predictive modeling. So in classification, we have a bunch of things, and they each have some known label or class. And the idea is we're going to have a new thing that we don't know the label, we don't know the class of, and we want to predict that class. So how will we predict it? Well, we'll look at our data and try to figure out what's the connection here so that we can come up with a predictor which has some good properties, like that it's right most of the time, things like that. So that's predictive model. We want to predict a label of an item given some training data. Third, pattern mining. So that pattern mining, I won't talk about today, but I'll just give you a little bit of idea of it for time reasons. So for instance, if you have some items and they are something like sets or sequences. So for sets, an example is in a store, let's say it's 7-Eleven or Tesco Lotus, a person goes to the cash register and they check out several items, right? So your shopping list contains several items. And so many other people do that too. So there's this list of sets, and each set is the things that were purchased together. So an obvious thing to ask is, oh, what are the most purchased items, right? But what frequent item set mining looks at is not what are the most purchased single items, because that's kind of a simple ranking task, but what pairs of things were bought together. And that's a little more interesting, right? What two things or what three things are very commonly purchased together right now. So frequent item set mining is a way to take huge lists of that kind of information from store purchases, but also there's other data that have this kind of tendencies. And we can find patterns, like for instance, if we find that people buy Coca-Cola and chips a lot, that would be kind of common and expected, but maybe the store would then, if people, maybe they put a sale on one of them and expect the sales of the other to rise. In fact, there's a very famous result from one of the first frequent item set. So when the algorithms were first invented, people were able to mine this data. They found that apparently that beer and diapers were frequently bought together. Some people think it's kind of funny suggesting that your dads would have both beer and diapers. Somebody else though that said that was not really true. It was just another example, but it's kind of a legend in the literature. So we can find those kind of things. Another would be association rules, which is kind of similar except when there is some sequence or some temporal set. So for instance, if a university takes a look at all the people who visited the university website and what sessions did they perform, well, they might be interested in link analysis, and in particular knowing what links on the site do people go to from one to another. So if a lot of people went from the university homepage and then visited the department page and then visited the engineering department, if that is very common and the data jumps out, then that might help them adjust their site to make it better. And you can imagine in e-commerce and in a lot of other cases, people would be very interested in what are the common links, the paths that people are taking. So this kind of pattern mining is about taking really big data sets like that and finding frequent patterns that emerge. But like I said, I don't have time to cover it today. And lastly, there's a whole bag of things in data mining that can kind of come up from finding outlier detection, graph mining, information extraction, and things like that. So a common theme of all these methods in data mining will be we want to extract knowledge from really large amounts of data, do it scalably. And so today, as I said, we'll just talk about clustering and about classification, because that's all we have time for. Okay, so let's start with clustering. So as we said, the goal of clustering is given this collection of data items, let's determine what groups they form. So for instance, if our data items are news articles, then if we did clustering on similar words in them, then we would find these clusters, these groups that would form topics. Like sports news articles would have a topic, a set of articles about each of a number of different sports. Or in a social network, users, by generating data about their activity, could be clustered and grouped together to form cohorts that are similar. So people have done these analyses, and you can see kind of groups of users that will have similar behaviors, similar characteristics. Or another example would be in shopping, customers with similar purchasing habits can form different groups, and we would want to automatically discover these groups from the data. Okay, so then state a little bit more formally, so the goal of a clustering algorithm is we're given a bunch of objects. We want to find the ones so that objects in each group will be similar to each other, and objects in different groups will be not similar to each other. All right, so here, with each point representing a data item, we can see it here, right? You can see where there are eyes, that there are 3 clusters of data, and then these clusters go together. So the goal again is minimize the distance between data items that are within a cluster and maximize the distance between items that are not within a cluster. So maybe we should stop here and just ask, does anybody have an idea like how we would do this? Right? This is a great example of something as a human, we can see it instantly, right? How many clusters are there? There's 3. And what's in each cluster? Well, 1, 2, 3. But if you think about it, so it looks like these are kind of in 3-dimensional space. So this is a list of points with an X, Y, and Z value or something. How do we know from that list? How can we know how to form these clusters? Any ideas? A common pattern in the list. Yeah, so they certainly have things in common, right? If you have one item and other items here have things in common with it, they may belong in the same cluster, right? Of course, in this case, there's not really any exactly on top of each other. It's more like they're close than they're exactly identical. Any other issues? If they're frequent, the frequency of them? Well, to form a cluster, we do need to have a number of items in it, right? If we had one point by itself, maybe we'd say that's not a cluster. So that's true. We do need maybe a frequent number of items in an area. I think it's very useful to think about. This is one of the great programs. A human can do it easily, but how do we teach a computer to do it? It takes some thought. So what I'll show you is, first of all, that commonly clustering algorithms, what they look at is some notion of distance between data items. So if you have 2 data items, we'll figure out some way to say, are they very similar or are they very non-similar, right? If they're distant, then they're far apart and not similar. And then we'll run some iterations where it tries to balance these 2 previous criteria. Puts things that are close together in the same cluster, put things that are far apart in different clusters. And so I'll show you how the most famous and widely used clustering algorithm works. It's called K-means. There's a lot of other algorithms out there, but this one is the most famous. And the good news for us is it's very simple and visual. So I'll show you how K-means clustering works. So the algorithm is this is the only algorithm in the talk. Right? So this talk has one algorithm and basically one formula. And that's it. This is pretty easy. All right, so K-means. The first thing we do is select K points as initial centroids. We're going to set K initial points. And then we're going to loop. And in the loop, what we're going to do is repeatedly, we'll form K clusters. By for every point, we'll assign it to its closest centroid. The closest to those K centroids. And then we're going to move those cluster centroids to the middle of the cluster of assigned points. And then we're just going to repeat. We're going to keep repeatedly doing that until things stop changing. So just a really 3-line algorithm. So let me show you visually how it works. It'll be easier to see. Okay, so this K-means clustering. So this is iteration 1. So you can see we've got some points here. And then these 3 crosshairs, each one of those is one of those what we call the K-means. All right, so we've assigned them to these initial locations. It can be, you can think of it as random, basically randomly having assigned them. And then what have we done? You can see for every point here, it's been colored with the color of the closest centroid. So for each point, it just looks at these 3, figures out which it's the closest to, and then we've given it that color. Right? So we can see you've got the red color at the top, the green in the lower left, the blue in the lower right. Any questions about what? I don't want to lose anybody yet. So far, can everybody see what we're doing? Okay, we've got the points, selected centroids. And then after assigning these points, remember the next step was we're going to move the centroids to the middle of the cluster. So, for instance, this centroid here, I mean, where do we think it will go? Yeah, down and to the left, right? Or in this direction. And we can probably see, for instance, because of the pole of all these blue points, this centroid is going to go down to the right. And so let's see what happens on iteration 2. So that's right, it moved. The green centroid moved down to the left, the blue down to the right. And also notice what happened with the third centroid. It moved to the middle of its cluster, but the green and blue, having moved, created some extra space. So it now has got sort of a larger chunk of points up top. And then we can imagine, okay, what do we think will happen in iteration 3? Well, actually, things will continue, right? Kind of the whole of these points down here will keep recentering these centroids down towards them. And then in iteration 4, 5, and 6, by iteration 6, we're done because things haven't changed. They won't change from that. And so this looks like a really nice result, right? If we had looked at this data, we'd say, this looks like the 3 clusters, and K-means has found the 3 clusters in 6 iterations. So we'll show again, this is just the 6 slides of each iteration. So a very simple algorithm. And it's really one of the most popular and effective. So even people that have come up with a lot more complicated algorithms, they don't necessarily always outperform K-means. It's still a really commonly used algorithm. Any like limitations, downsides, drawbacks, things this can't do that you can see from looking at this? I'll talk about a couple, but I wonder if any come to mind. So I'll tell you one first. In K-means, it doesn't always work out this nice. So we don't always have the centers move towards the clusters. Sometimes we might have to retry with another random assignment. And there's other various ways to kind of try to get this good result of correctly identifying the clusters. Sometimes 2 get stuck in one cluster. There's various problems like that. Any other thoughts about limitations? So I'll tell you one more. Another is that if the clusters don't really look circular like this, the K-means won't work very good. It tries to divide the data into kind of circular shapes, and that's because we're using closeness, right? And closeness is kind of something that lends itself to a circular shape. So there's a lot of other algorithms out there, and people have made little tweaks to K-means to try to get it to adapt to certain problems that but still really simple and really popular. Okay, so that's clustering. Any other questions about clustering? We got some data. We want to know who are the groups within it. Clustering is a great tool. Okay, so next day, my topic, classification. So classification, the goal is, as we said, we want to assign a data item to one of several predefined categories. So for instance, we could have a financial transaction, and we want to label it either fraud or not fraud. Or we can have a patient in the hospital. We've got some data about each patient, and we want to try to find, based on what we know about them, are they sick with some disease or not sick? Or lastly, something that all of us are really happy about is that classifiers can classify email as either spam or not spam. So these are examples of some of each of them. For instance, in this example, there's a credit card, and there's minuses for fraud and pluses for a non-fraud transaction. This is an actual example from patients, where the green are healthy patients and the red are sick patients. And over here, this is a spam example where red dots are emails that turn out to be spam and green ones that are not. You see these kind of lines and shapes between them. And what these are is a classifier. We've been trying to learn a classifier that will make a distinction between these two things. Okay? So kind of like in clustering, we can look at it and we can see here's some minuses, here's some pluses. And if we want to kind of distinguish, we get a sense of how we would do it, right? Based on the criteria we would see. Some kind of line here. Here the classifier learned that this squarish shape discriminates the healthy patients from the sick patients. And here with the spam email, it looks like non-spam kind of falls into this region below the line, and spam falls into the region above. So this is the idea of what a classifier is trying to do. Find the data and find some difference. Find some difference between the data. That can help us make these distinctions between two or more categories of things.
Can I have a question?
Yes.
What is the difference between clustering and classification? Very simple.
Yeah, particularly good question. Yeah. So the main difference between clustering and classification, you can remember in clustering, we didn't have any labels or classes. So we just had a bunch of data items like users or news articles, but we didn't know what each one was when we started. So with classification, things are different because at the time that we start, we know what the predefined categories are, and we assign them. And the idea is that we have some data that is already, I would say, labeled. For instance, if we want to detect email being spam or not spam, what we really have to do is start with a list of emails that we know are not spam, and a list of emails that we know are spam. And then we want our algorithm to try to make that distinction. But with clustering, we don't have that. Clustering, it would be more like you have a list of data items. We just want to know what are the groups. So if you know less about your data, then sometimes you have to do clustering. Or if it's very expensive or complicated to label it, then clustering would be like kind of more exploratory. But once you really know, what you're looking for, a classifier can help you make this, figure out what this distinction is. Any other questions? By the way, you might, clustering is known as the so-called unsupervised learning. We talk about machine learning, trying to learn this kind of thing, whereas classification is known as supervised learning. So that's kind of some terms that people, some lingo that people use. Okay, so the goal of a classification algorithm, the idea is we have this table and we have these features. So here, each data item is a row. So we have this information about each data item, and it's got a label, like A, B, or C, 1 or 0, something like that. So when we have these, now what we want to do is have our classifier learn this relationship between this set of features, each set of features, and each class, in a way that will let us discriminate between classes. So we want to learn this model. That's the goal of the classifier. From this, we'll call training data. We want to train our model. So just to give you a little bit of intuition about what kind of models are out there. For instance, if we've got different groups of things, maybe we want to try to find this kind of linear separating. So it's a little bit like regression, except, in regression you have some pattern you want to kind of draw a line through it. And here with classification, you want to draw a line between different things. That's the goal. Because if we can figure out this line, then we know that things above it tend to be one class and things below it tend to be the other class, right? We get a new item and we just plug it in as X. And we figure out what the Y is. Well, if it's high enough, then it's this one class, otherwise it's the other. But others are not that simple. They can be curved shapes instead of lines, or even a circle. And then lastly, a model doesn't need to be some kind of general equation. It can also be, for instance, this is from a kind of classifier called a decision tree, where it's kind of like a flow chart. So you start at the top and follow some of these conditions down. And when you get to the bottom, in this case, it predicts somebody's either healthy or sick. So this is learned from data, just like each of these repeated. So if you have a bunch of data and you want to make these kind of decisions, you can try it out through a classification.
It can do only the decision, or like we can have only like two different data, or like more than two.
Yeah, I think you're asking, can we just have two classes, or can we have more than two?
Yeah.
There can be more than two classes. For instance, here there's 3 classes, A, B, and C. Even though the previous examples were all 2 class, I just wanted to show that it was possible. But usually people will kind of start out with this kind of 2-class situation, like, oh, it's either spam or not spam, not some third thing, because it's simpler. So we call that binary classification, because there's 2 cases. But there can be multi-class classifiers also that try to discriminate. Or another thing people do is they would just have a binary classifier for each of the possible classes, like is it A classifier, is it B, or is it C in this case. So there are a lot of possible variations. But yeah, the easiest to think about and start with and stick to is just binary classification. Is the patient sick or they healthy without worrying about it?
So is it like, if I have no idea about the data, I use the clustering, right? So after that, it's giving me some clue about like the difference between the data, and can I use the class after that? Classification after that?
Sure, yeah. The question, in case you couldn't hear, was could we start off doing clustering, maybe because we don't know much about the data to explore, and then do classification for some reason? Yeah, that's pretty common because, for instance, so here we talk about predefined classes are known, but you might start out without knowing classes. So if you can kind of learn that, all right, I'll do clustering and find out what the groups are, and then you can build a classifier to try to predict the groups. So that kind of data exploration process, or pipeline, where you do one data mining algorithm and you use the output as the input to another data mining algorithm, is pretty common. But that's a very good insight, because a lot of times we don't know that. That even reminds me that I could back up and say some things about clustering algorithms like k-means. We can start to now see some of the limitations, because, for instance, here we need to know how many clusters there were when we began. But in real-world data, we might not know, right? How many groups are there? We don't know. And sometimes the clusters even have some hierarchy. So you have kind of a big cluster that has within it subclusters. So is it one or is it many? And when you get into those kind of questions, there are tools to help make decisions, but also sometimes you need to have expert opinion. So you ask a doctor or a journal, whoever's in the domain of the data you're working with, and they can help tell you that, oh yeah, here's how we think about the groups of things. A lot of times that can guide us.
Can I have a question on K clustering? What is the optimum value of K? Because we haven't set K, right, in the group. So what is the good value for K?
Right, the answer is depends on the data, right? So for this data, clearly K being 3 is a great choice, right? If we chose K of 2, we would just have 2 of these crosshairs, and probably one would end up here and the other would end up down here. And if we chose K as 4, then probably one of the clusters would be split between. So there's this kind of notion that, okay, your best value of K is 3. But you notice that in an algorithm, K is not something that is changed or discovered in an algorithm, right? So we call it a hyperparameter of the algorithm often. It's something that's fixed, and then we run the algorithm. Any ideas of how you might pick a good K? How would we know how many clusters data has?
In this case,
Any idea?
You have data, how many different groups of things are in the data? Any ideas? Frequency. So what does that mean? how would we use frequency?
Not sure what the Y means.
Yeah, here it's kind of abstract. I mean, this could even be higher dimensional data than 2 dimension, right? You have 3 or 4 or 5 dimension. But there's some space and the data is spread across the space in some way, right? And we want to know where's the kind of cohesive groups in the space. It's actually, it's quite difficult, really. And it's not an answer that has any one question, because again, it depends on the data. Like you can imagine these are 3 nice tight clusters, but what if one is very spread out? And what if one is very tight? And what if one is very big and another is very small? So there's a lot of cases where, maybe to our eye, we could probably see what is the right grouping. But to try to get an algorithm to figure it out could be difficult. So, but I'll mention maybe one thing you could try. What if we just try k-means over and over with different k? We try with k equals 1, k equals 2, k equals 3. And then we try to see which gives the best result. And you ask, well, how do we know which gives the best result, right? If we can't visualize it. So we can't visualize it. It's very high dimensional, and there's a billion points instead of the 100 that are listed here. Well, maybe we can look at some measure of the gradients of these. Right? That's something people commonly do. Because the thought is, if all your data points are pretty close to your center, then you probably did a good job. But if somehow you have I don't have any bad examples here, but they exist in the literature. If you have points that are very spread out, even when an algorithm completes, and you kind of add up the distances from points to their center, and that number is very big, then that's not so good. Right? So maybe we run a different k, and we pick a k that gives us the type score. So this is one idea. Why is k-means so commonly used in accuracy? It depends on the data. So sometimes accuracy, sometimes it does do a really good job. Yeah. If the data is well separated, so if these are pretty far apart, like this, or further, and if the clusters are kind of tight and circular, then k-means can do a great job. But again, if they start to overlap or have other problems like that, you can't. But also, some data is more inherently noisy than others. So it could be a good idea to try several different algorithms. And I'll mention some toolkits at the end that are just suites of data mining tools. You get your data set, and you can try k-means, and you can try dbScan, and a whole bunch of other algorithms, and then just see what the results are. It's common to need to do that, especially when we don't understand the data or it's kind of new. Thanks for the great questions. Okay, so back to classification. We want to build these kind of models. We'd like to build models that can take the features and predict a class, right? So let me tell you 2 important things that we want in a model when we try to learn from data. So one is that we want the model to be accurate, right? If we're predicting whether people are sick or not sick, we don't want the model to be wrong. Now, of course, even a human doctor would be wrong. So we can't expect the model to be perfect, or maybe not even to be much better than a human expert would be. But we want it to be right a lot of the time, as much as possible. And the second criteria is that we like the model to be simple. Well, I think it's pretty obvious why we want the model to be correct. But why it should be simple might not be as clear. There's some nice properties to simple models, like you can look at them and understand them very well. You can be able to tell why it gave a result. Because there's a lot of models out there that are really complex. You run them, you get a result, and if you ask, why did it predict that the patient was sick, or that the email was spam? And going back and tracing that backward can be very difficult if you have a complicated model. Whereas, say, like a simple model, let's say if you have a linear, you just have a line separating your space, that can be very easy. But there's kind of a trade-off between these two. So data mining is about a lot of these kind of trade-offs. You can take this data and learn any number of different kind of models, but we like one that has these 2 criteria. It's correct a lot, and it's also simple. Okay, So like I showed you with clustering, I'll show you one classification algorithm that's really widely used and is no simple. So the goal, again, we want to learn some association between the features in the class. And we want to encode this in a predictive model that we can use to make predictions about new items that we don't know the class of. So one of the simplest algorithms for doing this is called naive Bayes. And it's just based on counting. All we do is count how often certain values show up with the class label. We make some fractions and call them probabilities and get some numbers and make a decision about which class it is. So I'll show you an example. And this is very high level, right? Just to give you the idea. So let's say we have this, we've got here 20 animals. And these animals have 4 characteristics about them. It's whether they give live birth, whether they can fly, whether they live in water, or whether they have legs. And then let's say we have this 21st example where we don't know what type of animal it is. So the types we're considering, we're just saying they're each either mammal or non-mammal. Right? So you can see some are mammals, some are not. And let's say we want to predict whether this unknown animal, which we know that it gives birth, it cannot fly, it does live in water, and it does not have legs. How can we predict its class? And it's worth stepping back and thinking, yeah, how do we do that? I mean, again, right, we call it a frequency, or commonality, right? For instance, suppose we found an example where the animal gave birth, couldn't fly, lived in water, and didn't have legs. Well, maybe we just make the same guess as that thing, right? But actually, if you look at the data we found, we don't quite have that. We don't have any one example that looks exactly like this. But there are some that look kind of similar, so we have some hints. So let me give you the kind of the results of what we do with naive Bayes. So let's first consider, we want to know whether this thing is a mammal. So out of the 20 animals, 7 are mammals. If we go and count them, so I've highlighted all the mammal animals here. So then we'll look at one thing for each of the features. So first we'll look at, does it give live birth? So if we go and count among the mammals, the highlighted yellow rows, which give birth, yes, we have 1, 2, 3, 4, 5, 6. So 6 of the mammals give live birth. We counted 6 for that. And then we'll find how many cannot fly. How many of the mammals cannot fly? Because we want can't fly as well. We find 6 of them cannot fly. So look at this again, fly column. 2 of them live in water. If you look at the water column, yes and yes for 2 mammals. And then 2 of them do not have legs. This is our test site. Okay, so we've got these count numbers. And these are all we need to make the prediction whether it has mammal. So the naive Bayes formula, the presentation has one algorithm with one formula, right? This is the only formula in the presentation. We take the 6 out of 7, because 6 of the 7 mammals can give birth, times 6 over 7, because 6 of them cannot fly, times 2 over 7 live in water, times 2 over 7 have legs. And then we multiply by 7 of the 20 animals are mammals. This is something called the prior, just because out of all the animals, 7 out of 20 are mammals. And we get this number, 0.021, probability. So this is the probability, posterior probability, it's called that it's a mammal. And then we repeat this whole thing for the non-mammal case. In the non-mammal case, we have 13, and so on. We do this counting. And if we do this equation for the non-mammal case, we get 0.0027. So the probability that it's a mammal is higher, because 0.021 is bigger than 0.0027. So we would predict that this animal is a mammal. So that's it. I mean, there's a lot of details about why you do this kind of formulation and so on. But I kind of wanted to show you that it's not necessarily difficult, right? This is a pretty powerful thing to be able to do, to be able to make a prediction and classify based on these 20 data records, or it could be a billion data records. You can see all just based on counting. Making some counts, doing a little bit of multiplication, and comparing some values. That's it. Okay, so like, what have I shown? What am I trying to get across here with data mining algorithms? So clustering and classification are 2 of the major data mining algorithms that we use. We showed k-means clustering which is a simple algorithm based on just moving centers. Just moving centers, move. In 90 days, it's a simple classification algorithm based on counting. I'm just going to come up with some counts and do some multiplication. So both of these are pretty easy to understand. And small examples can be solved by hand in 15 minutes. And I know this because in the data mining course I used to teach, we have questions on the exam about that. And students could do that, so we could do that. You could answer small questions in that amount of time. They can also code up implementations in about an hour once you're really familiar with algorithms. And this is not just something to be done, but it's somewhat of an expectation too, which I know because, for instance, I've been asked to implement K-means on a shared screen as part of an interview process for a large tech company. So they're simple enough that they can be written up in those short amounts of time. Something I didn't show you, but I'm telling you, is in practice, people found when they apply to real-world data, they do get good results. So that's really nice. They're simple, and they also give good results on purpose. And part of the simplicity kind of brings us to the next topic, which is that they're easy to, because they're so simple, they're easy to scale up to handle a lot of data. Okay, so let's talk about that in the second part of the presentation. Any remaining questions about the data mining, about classification, clustering?
So the number you calculated